Good afternoon. I am Federica Filippini from Politecnico di Milano. This video will give you an overview of the AI Sprint Scheduling for Accelerated Devices component and its main contributions. Traditionally, an application manager willing to run resource-intensive deep learning applications on accelerated clusters has to perform an estimate on the type and number of GPUs needed to complete the execution by a prescribed due date. Moreover, cluster resources as GPUs are often dedicated to run single applications, causing significant underutilization and higher costs. Scheduling is usually demanded to first in, first out, or earliest deadline first algorithms, which are unable to effectively cope with different job priorities. The scheduling component we developed in AI Sprint overcomes these limitations. After a short profiling, which is performed the first time an application is submitted to our system, the job execution time under different resources configuration is predicted using machine learning-based performance models. These predictions are used to automatically select the best configuration for each job, given by a specific virtual machine type and number of GPUs. Our scheduler defines the best configuration as the one minimizing execution costs without violating the job due date. During the execution, jobs can be preempted to free resources to other applications with higher priority. Our component supports the execution of artificial intelligence training jobs executed in GPU-accelerated cloud clusters, minimizing the costs due to virtual machine usage and the penalties for due date violations. The scheduling for accelerated devices handles the complete training process, starting from the collection of execution profiling data. When a user submits an application to the job manager, this checks whether execution information are already available in the component database. If not, the job is deployed to correct profiling data, which are used together with machine learning-based prediction models to estimate the training time on different virtual machine types and resources configurations. All the relevant information, including the cluster description, are sent to the job optimizer, which determines the optimal scheduling for all jobs in the queue. The job manager uses the job optimizer response to instruct IAM on the resources to be deployed so that the scheduled applications can be executed in the cluster. Here is a sketch of how the job optimizer works. Submitted jobs come in the form of Docker containers and are inserted into a queue. The optimizer combines the predicted execution times and the cluster description to select the optimal virtual machine type and number of GPUs to be assigned to each application. The execution logs are collected to periodically retrain the performance prediction models. The optimizer is called periodically and every time a job is submitted. The resources assigned to each job may change over time to accommodate other applications, always trying to limit migrations to avoid overheads. If the available resources do not allow to execute all the submitted jobs concurrently, some can be preempted and returned to the queue, waiting for the next scheduling point. We adopt a checkpointing mechanism to resume jobs without losing the training progress. Our job optimizer implements different scheduling algorithms. A base grid method that sorts jobs according to how close they are to the due date and selects for each application the cheapest available configuration that avoids violations. A randomized greedy algorithm implemented by randomizing all decision points and selecting the candidate with minimum total cost. And a path relinking algorithm where an enhancement strategy is included after the randomized construction procedure. These are some of the experimental results we achieved testing the job optimizer considering heterogeneous training applications. We compared the performance of our method with first in, first out, earliest deadline first, a hierarchical method we had developed in the past, and a dynamic programming-based method adapted from the state of the art. We considered different patterns for job intervals, which are shown in the picture on top. The three plots show the average total cost achieved with different methods. We can observe that our path relinking approach is the one performing best in all scenarios, achieving a cost reduction between 20 and 95% with respect to the others. Now I will leave the floor to our colleague Maciej from 7Bulls, who will demonstrate the use of our scheduling components.
Hello everyone, my name is Maciej. I'm the developer at 7bulls.com. Today I will show you a short demo on GPU Scheduler, and to be more specific, the goal of today's video is to show you the flow and the usage of the platform itself. So I think we can go directly to the diagram where we can see the diagram of the components, and the main part is the platform itself. Pretty much is what you can see in the top left part of the diagram called control unit. There we have two main components, the Jobs Manager and the Optimizer, that pretty much use the entire logic of the platform is hidden there. I will go more into details of it a little bit later. And on the top right we have the workers that will be used to run our jobs. As the main goal of the GPU scheduler is to receive the jobs and to execute them on virtual machines containing GPUs. And as you can see on the top left, the flow would look like this, that the client submits the job or multiple jobs. They are later processed by Jobs Manager, which calls first jobs to be executed on nodes during the profiling step. And this step is the part where we gather data on the jobs themselves. So we would have more information how or what resources we can find, what resources we can use for to perform them the most optimal way. And this information is returned to the optimizer, which makes pretty much the decision of what resources we can assign. So for example, during profiling, it gets data of different runs, and optimizer can make the decision that, for example, for the specific jobs, it is better to use the Kepler GPU instead of 3 Tesla GPUs, for example, that will have a better performance, and it will be better to run those jobs prior to the others to meet all the deadlines. And this real training is done during the training part, where these jobs are run. So this is pretty much our entire flow, from client submission to the jobs being performed to the job producing model, because the jobs are machine learning models. We are using TensorFlow, so these are Python 3 TensorFlow machine learning scripts. You can also see here this cloud at the bottom. This is the platform infrastructure manager. We use it for the setup of both GPU scheduler, both the control unit, and all of the workers that are necessary. So we can define how many workers we have. An infrastructure manager would set up this configuration and would later have the ability by the GPU scheduler. If GPU scheduler decides, it can call to infrastructure manager to start or stop the workers. As the entire setup is done automatically, I want to show you how it is done, as it is very simple. Here you can see the API of infrastructure manager, where I have a list of multiple files that are pre-prepared, and here you can see the pre-prepared file .riedl that explains how to set up the GPU scheduler. So pretty much this can be copy-pasted. If you want to, here it is defined to use my AWS account, so we'll have both GPU scheduler and workers running in AWS. The only thing you can change pretty much, and is worth changing to suit to better meet your needs, is here the setup of the workers. As you can see, I will have one control unit that contains GPU, Jobs Manager, and the Optimizer. I will have one big worker that contains of two M60 Tesla GPUs, and the other combination of single GPU M60 and T4 GPUs. And the only thing I need to do now is to save, run it. Here you need to put the credentials. I skipped this so we don't waste time, but I want to mention that here I put the credentials of my AWS account and the credentials of Infrastructure Manager, as GPU Scheduler needs to have the ability to communicate with Infrastructure Manager to indicate where we want to start or stop the machines. And the additional setup is the passwords we want to use for workers or the control unit if somebody wants to connect by themselves to those machines. Okay, and the only thing left is to launch it. And now Infrastructure Manager automatically would set up the entire platform, and the only thing we need to do is wait. You can see we were redirected to the screen of the setup, and yeah, this setup would take around 20 minutes, so I think we can skip this part, so I will see you in 20 minutes. Around 20 minutes have passed. You can all see the deployed message on configured message in Infrastructure Manager and the list of all of the virtual machines that were started. We can indeed verify it in my AWS account that I have all the workers running, and as well also control unit containing Jobs Manager and the optimizer. The important thing that we need to get, we can see here all the details of the virtual machines in just a few seconds, but the important thing is that we need to copy IP of the control unit, as Jobs Manager and GPU scheduler let us connect to it via REST API. So we'll use this IP. I will use Postman for communication that allows us to send messages to JSON messages, and I will submit a job to show you how easy it is to do. But first, after starting the platform, we need to specify the setup of the workers. As I mentioned before, we have four workers, and here by sending this message, this node configuration, I can specify what is the cost of the machines of using this worker, and also the important part is for profiling flag, indicating if the nodes would be dedicated for the profiling step or later for the training. Know that it can be changed anytime you want, and we will do so later. At this moment, I will start with two nodes dedicated for profiling, worker 1 and worker 2, and the other will be meant for training. So I can send this, getting the message back that the nodes were updated. Okay. Now I will submit two jobs. There will be both LS team jobs. That's goal is to produce model that can predict values of euro to USD. We can have a look at such a job. I will show you the script of the LSTM one. And as you can see here, this is the machine learning Python 3 TensorFlow script. The majority of it is creating the model itself, training neural network. Here, this is the LSTM neural network, as you can see here. And of course loading a training set, which here is the historical value of euro and USD. Important thing to point out is that there are a few small requirements for such a script so that we can benefit 100% from the GPU scheduler. And here this is the ability to load the pre-trained model, and of course later to save a newer one. This is important as the ability to create snapshots enable us to stop training and then restart it from the same place in a different virtual machine. So here you can see it, loading the model, and at the end there is saving it. Those snapshots are stored on the network file system, so they are shared. They're shared between among all of the virtual machines, so that every GPU has access to them. And of course, we have some environmental variables indicating how many epochs we need to perform, and some additional properties like batch size. Okay, let's get back to the request. I want to show you the details of the submission here. The important part, of course, is the job ID, as you can see. Later we can specify the job itself, so the script name that I will need to upload in a few seconds, and also Docker image. We recommend to use the pre-prepared TensorFlow image, but you could use the different one. Also, the important part is deadline, and the priority. Those are the information for the optimizer to make better assignments. batch size is the environmental variable for the job itself that can be used, and also the important part, profiling epochs number and epochs number at total, meaning how long we want to train, how many iterations of training we want to have. For profiling I chose 2. I think this is sufficient to gather data about the job, and later the real training would be running. As I mentioned before, we need to upload needed files. So for LSTM, this is of course our Python script that we upload. Also the historic data of prices of Euro and USD, as we will need to use it for training. It's uploaded, and we'll do exactly the same for the second job, LSTM big. Okay, I mentioned two jobs, LSTM small and LSTM big, but know that I will launch a total 4 instances of those. So I'll launch 2 instances for LSTM small and 2 instances of LSTM big, because as I mentioned, we use the profiling data, and this profiling data would be reused when we will submit the job of the same profile, meaning pretty much the same job, but probably with different configuration like batch size or epochs number. So here I will submit 2 instances. As you can see here, I get the idea of the instance, and 2 instances, a total of LSTM small and 2 instances of LSTM big. Yeah. Okay, now we'll navigate to the logs of the jobs manager. Note that this is transparent. Note that this not necessarily needs to be used by the client, but that gives us a good information about what's happening in the platform. As you can see in the logs, here's the current situation that is running, and as you can see, a few of the jobs are going to be assigned for profiling in just a few seconds, and LSTM small has already started. You can also see the progress bar and the assignment, so on what worker it is running and with how many GPUs. Okay, and after profiling, we'll move to the training part. And I think we can, in this moment, we can wait a little bit, so we'll skip a few minutes to see the progress that's been performed. We are back after some time, and in this part I want to show you what has changed, as I haven't interfered in the job's execution at all. So I want to show you what's the current state of the job execution. We can traverse to the logs. Here's the current state. And as you can see, the profiling has been finished. We gather all the data about all of the jobs. You can also see that progress has increased, so we have multiple epochs performed. And as you can see, even though we have only 2 workers available for us, still we made progress on all 4 job instances. And this is because the optimizer makes the decision, for example, to change the resource, to assign the resource for some other job if it finds it's necessary. So here it gave some time to all of the jobs, and this moment you can see that the second job big 4096 is the closest to the end. I will show you in a few minutes. I will show you in a few minutes that we can indeed see already models that were created. But I want to stop here to show you that, as I mentioned before, the profiling has been finished, and the result of this is that we don't need those nodes, those idle dedicated for profiling nodes anymore. So GPU scheduler can make the decision to stop them. And as you can see, we have still 2 nodes running and 2 nodes in a stop state. It means that when they were idle for too long, Jobs Manager decided to send an information to Infrastructure Manager to stop not used nodes. As you can see indeed in my AWS account, 2 of the workers, those are the ones dedicated for profiling, are currently in stopped state, so we can save the resources. This can be easily switched back on, and will do so by simply submitting another job. So now I have a choice. I could, for example, switch those nodes to the running states to give more resources for the optimizer to run all of the jobs. But I will simply upload another job. Once again, with the same data. Yeah, and this one would also require profiling. So currently all the nodes for profiling I stopped, and they should in few minutes be started again, and the profiling should start on them without any problems. It will take a few minutes as I need to communicate with them, but you can already see that one of the workers in a pending state, meaning that the information has already been sent. In the meantime, I want to show you the models, as every script is encouraged and it's necessary to produce models after each epoch, which gives us the possibility also to use it as a checkpoint. So whenever any problem arises, whenever, for example, a job crashes for any reasons, we can simply start from the last checkpoint. And here we are in a directory of working directory of one of the nodes. We have access to it, and we can see what are the files inside. And here we can see, of course, the input files, and also the logs and the output file that gives us an information of what's happening inside the job itself. But the most important part is this model that was created. This is our checkpoint, and this is a working model, so pretty much we could from this moment we can download it and use it, because this is a working model. But of course our goal is to have 15 epochs, so we still need to wait a little bit until a model with 15 epochs is created. I will now go back to see what's the state of our workers. Yeah, and it seems that they're running, so I think we can go back there and see what's happening inside. Yeah, and this is the current state, and as you can see, the training jobs are still running without any issues. They're still progressing. You can see all the nodes in the starting state, in the running state, and indeed the job we just submitted runs properly its profiling step. This will be all, so thank you very much.